undergraduate at the University of Berlin. He was a graduate student at Stony Brook, where he actually worked on supergravity. He's a postdoc at HgTe, research staff member at the IBM lab in Alden, and since 1993, he's been a professor of physics at Stanford. Since 2010, he was J.G. Jackson and C.J. Wood Professor of Physics. He's made a number of contributions all across condensed matter physics and the boundary with particle physics and field theory. They include work on high-temperature superconductivity, spin transport, and what I think you will tell us about today, which is topological insulators and superconductors. Every aspect of the field of topological insulators bears his imprint, and he has recently been recognized for that work by the Europhysics Prize, the Dirac Medal, and the Bunting Prize of the American Physical Society.
Thank you so much, Bill. It's a great pleasure to come here to Berkeley and to give you a talk and maybe to give an update on this very interesting field in condensed matter physics. It's also a very special honor because I see my colleagues, Joe especially was an early pioneer of the field. Ashwin, your theory colleagues Ashwin and Heidi did a lot of work. I also work very closely with Joe Orenstein. In fact, we have a POE project together. So the subject of the talk is an interesting new state of matter. Maybe by now it's not that new, but still it's quite a fascinating state of matter in condensed matter physics. It deeply relates. I think the reason a lot of people got interested in is because it deeply relates to some beautiful mathematical concepts going back to topology. And mathematicians like to classify shapes into general and broad categories. And the most interesting and profound concept they come up with is the idea of topology. For example, American football and the European soccer ball will be viewed as more or less the same in the same class because they can be smoothly distorted from one to the other. On the other hand, when you look at a coffee mug and a donut, they belong to yet another class. They deform continuously into each other, as you see from this animation, but they can not be deformed into either European soccer ball or American football. So this is the idea. There's some topological invariant. There's something that doesn't change as you make smooth distortions. So these concepts, somehow it looks very abstract, but these days it's at the frontier of mathematics research. A lot of the work is done here at Berkeley, but somehow it connects to materials we can feel and we can do experiment on. This is the cartoon picture of the first topological insulator discovered in nature in mercury telluride quantum wells, where the electrons don't move in the interior of this two-dimensional heat, but they move at the boundary with a very well-defined pattern, whereby the upspin goes around in a clockwise fashion and the downspin goes around in a counterclockwise fashion. So as if the electrons are executing an ordinary motion in this system. And there's also a three-dimensional example of that you can take a chunk, this time not something that's confined to an interface or semiconductors, but a chunk of three-dimensional material where it doesn't conduct on the interior, but on the surface, they have actually a wonderful surface state whose energy spectrum follows that of the Dirac cone. This is actually real experimental data. Looks almost too beautiful to be real, but it is experimental data performed, collected at SLAC, showing the surface state of a material business area. And all these things that you can do experiment on with the state-of-art technology, but also deeply relates to the concept of mathematics. So that's kind of fascinating, and I hope towards the end of the talk, I can touch upon the possible application of these materials. So we're in the field of condensed matter physics, and you will always ask, what is kind of the fundamental pursuit of our field? So in particle physics, in chemistry, in chemistry to 100 years ago, in particle physics starting maybe 50 years ago until now, there's two basic trends in science. One is try to find smaller and smaller building blocks of matter, and the other is that given the same building blocks of matter, how are they together formed to form interesting different states of matter? So for example, the golden age of chemistry is to discover the elements, the basic building blocks of matter. In particle physics, we try to discover more and more elementary particles, the latest being the Higgs particle. But we're in a different field, where given the same kind of Lego pieces, we wonder what kind of interesting manifestation of when they put together, what kind of new states they can form. For example, if you take ice and water apart, down to the smallest building block, they're exactly the same. But when they're put together, Theo Anderson has the famous quote of more is different. As you put more and more of these basic building blocks together, you get to wonderful new things. And as human beings are also made of atoms and electrons, but somehow there's emergence of a new structure. And that is the kind of structure or new states of matter we try to study. And it's an example for the collective emergence on the individual behavior. So now we have found many different states of matter. For example, we have semiconductors, magnets, and superconductors. And after we discover more and more of them, we try to discover some organizational principle, which how do we define them in a simple and unique way. And that gave birth to the idea of a spontaneous broken symmetry. And in a crystal state, even though the elementary interaction between atoms is translationally invariant and rotationally invariant, but inside the crystal, the orientation actually, you can only rotate by some discrete amount, you can only translate in a discrete amount. There's symmetry, even though the basic interaction doesn't break the symmetry, the particular state of solid break this symmetry, and that's how we define solid to be something different. And also in magnets, basic interactions are rotationally invariant, but in magnets on Earth, we can tell north from source because a direction has been spontaneously picked up. In a superconductor, the symmetry that gets broken is more subtle, but still it breaks the symmetry. But after that, you may wonder, what is the basic pursuit of solid-state physics anymore? Because it's just discovering more of these states, but they are more or less follow this very broad principle classifying states of matter according to this order or spontaneous broken symmetry. So what changed recently is there are new states of matter which doesn't fall into this paradigm. And the first discovery of the kind of a topological state is actually the quantum Hall effect. So I try to explain this from a very basic elementary equation of 2 = 1 + 1. So imagine that you are in a one-dimensional world, in a one-dimensional wire. For the moment, forget about the fact that electrons have spin. But still in the one-dimensional world, you will have 2 ways of moving. You can move forwards, or you can move backwards. So there are 2 different ways of moving in one dimension. And that's, so as long as you're in one dimension, and for the moment forget about spin, you cannot get around them. But that immediately leads to resistance, for example, that if you have impurity here, what was happily marching forward, the electron there can be backscattered. So any one-dimensional wire would have some resistance. So that state is maybe not so interesting. But there's a very interesting way to decompose these 2 types of motion into 1 + 1. Imagine now we have rather than a one-dimensional system, but a 2-dimensional system. But the electron doesn't move at all in the interior. But then one branch, which is the forward branch, is confined on the upper edge of the 2-dimensional sample, and the backward moving branch is confined on the lower edge of the 2-dimensional sample. So now you may wonder, how do the electron tell a sense? That is, the sense is told by external magnetic field. So for example, if I have a right-handed rule, if my thumb points into the plane, then my fingers will kind of sense that there's a circular sense, clockwise circular sense for the electrons to move around, and then the electrons on the upper edge will know to move forward, and then electron on the lower edge will know how to move backward. So in this case, it actually leads to a dissipation-less transport on the edge, because of this fundamental equation of 2 = 1 + 1, because you only have one branch on the upper edge. This is really like a highway system where the counter-moving traffic are spatially separated into different lanes, right? So now if the electron hits an impurity, then it becomes almost impossible for the electron to scatter to the other side, like jump all the way to the other side of the highway. More precisely speaking, we say the electron wave function is exponentially localized in this direction at the edge. So its overlap with the other edge is vanishingly small, exponentially small. So in physics, we don't look at this exponentially small effect. So then if you encounter some obstacle, you will simply go around and keep on moving forward. And that's the wonderful thing, that you have a dissipation-less transport, and experimentally it manifests itself into a precise quantization of the Hall effect and the vanishing of the longitudinal resistance. So in condensed matter physics, we only have two types of dissipation-less transport. One is realized in a superconductor, and the other is at edge state of these interesting quantum Hall states. So you will say, well, if it is so useful, having a dissipation-less transport, why don't we see that in devices you can buy in price electronics? Because this state is only realized under two extreme conditions. One is at very low temperature, and the other is at very high magnetic field. Very hard to imagine we have some device operating at high external magnetic field. So here is now a new idea how to generalize from quantum Hall effect to something called quantum spin Hall effect, or more explicitly, how to generalize the equation of 2 equals to 1 plus 1 to 4 equals to 2 plus 2. Okay, so the basic idea is that somehow, in order to execute this regular motion, the electron has to have a sense of orbital motion. But this, of course, the external magnetic field provides a sense. But let's remember, after all, that the electron also carries spin. So spinning can become an internal compass to direct the orbital motion of the electron. So now if we put the spin back together, in a one-dimensional world, you will still have 4 types of basic motion. You can have spin up or spin down, forward or backward motion. So you altogether have 4 types of motion. But now in this interesting state, it gets decomposed into 2 plus 2. In a sense that upspin, it's as if they're executing a clockwise motion, and as if they're seeing an external magnetic field, which is, let's say, pointing into the plane. But the downspin is like seeing the opposite sense of magnetic field. So they're moving in exactly the opposite direction. So Charlie Kane and Malik came up with an early model based on graphene. My group with my then student, Andrew Bernovic, came up with independently with a model on strained gallium arsenide, even though the earlier proposal didn't quite realize. I will tell you which one does realize that this basic concept is to use spin orbit coupling to provide an internal compass so that the electron will know how to move around. So this idea of spin orbit coupling is intrinsic to the Einstein's theory of relativity. So we know electron has a spin, and that acts a little bit like magnetic fields. If you make the analogy to the solar system, the Earth goes around the sun, and the Earth spins by itself every 24 hours, but it goes around the sun in 365 days. So for Earth, it's not so strongly coupled. Actually, very interestingly, for Moon, the orbital motion around the sun and its self-spinning is actually coupled. That has something to do with the earlier geological formation of the Moon during its molten state. Let me not go that much into detail. But basically, you have a spinning motion of the electron, and you have an orbital motion around the sun. And in this case, the analogy is that the electron has a spin, but it goes around the atomic nucleus. So as it goes around the atomic nucleus, if you take a relativistic point of view, if you sit on the reference frame of the electron, the nucleus has a positive charge. It will be moving around the electron. If you have some charged particle moving around, you will generate a magnetic field. But then magnetic field will be coupled to the spin of the electron. And so the theory of relativity actually not only qualitatively, but also quantitatively predicts that there's always this effect of spin-orbit coupling. So not only it's a qualitative effect, actually it quantitatively predicts that the order of magnitude of the spin-orbit coupling scales with the atomic number to the 4th power, z to the 4th power. So this actually tells you that this kind of effect, why the early proposal didn't quite work out, is because they are all somewhat lighter elements. And we actually first predicted theoretically that the right place to look will be in a system called mercury telluride. So this is a standard chart you see a lot in offices of optoelectronic engineer or semiconductor physicists. It plots the binary semiconductor in the space of energy gap, which is very, very useful. If you want to construct an optoelectronic device, from the energy gap, you can directly read the wavelength of the light it will generate. And so that's very useful. On the horizontal axis, people usually plot the lattice constant, and then people can put heterojunctions together because they're more or less lattice matched, so they know they can construct interesting material by stacking them on top of each other. But one day, as we were staring at this graph, we suddenly noticed there's something very, very strange about these plots. That actually there's absolute zero for the energy gap. That there's a sense that some materials, all these materials have a positive energy gap, but there's only one very strange material among all these binary semiconductors that in some precise sense has a negative energy gap, which is mercury telluride. And as you heard from Joe's introduction, I was a field theorist when I was a PhD student. So I learned a lot about quantum field theory. And one of the strangest results I remembered from that time is that in 2 + 1 dimension, when you integrate out some massive development, you get an effective transience theory, whose coefficient depends on the sign of the mass. So that's something in the background of my thinking, that somehow when you change the sign of mass, it could lead to a topology change. And that was the moment when we realized that there's something very, very special going on, that nature actually gave us a wonderful, wonderful gift that we can realize these new topological states. So actually, ever since then, this basic principle of a band inversion or negative gap driven by spin-orbit coupling has become by guiding principle. In condensed matter physics, almost no superconductor was ever predicted. But in topological insulator, almost every topological insulator is theoretical, based on these very simple principles. That as spin-orbit coupling becomes strong enough, when you drive a band inversion, it leads to a new topological state. Now, after all, what is this band inversion? It's actually very simple to explain. From basic atomic physics, in atom, you will have some S level and you have some P level. So, but under spin-orbit coupling, the P level will split. Actually, I had a nice chat with Bob. During his teenager time, you only thinking J. A lot of us grow up, unfortunately, thinking about L, which can get us very confused. But under spin-orbit coupling, the P level will split into P3 half and P1 half. And then this S level broadens into a band, this P3 half broadens into a band, and that's the usual conduction band and the valence band of most semiconductors. But now let's imagine that you go to higher atomic number, then this spin-orbit splitting will get larger and larger. But at the same time, there's another interesting relativistic effect called the Darwin effect, which the spin-orbit coupling will only act on P, not S, but there's another term, which is roughly of the same order of magnitude called the Darwin term, which only acts on S, but not on P. That pulls the S level down. So the net effect in mercury telluride is that this P3 half level now jumps above the S level. And when you look at the electronic structure, this P3 half level now lies above the S level. And this is the basic mechanism called band inversion driven by these relativistic effects. So now this enables people to construct a very interesting system. You remember from the previous chart that scanning telluride and mercury telluride are very well lattice matched. One is ordinary material and the other has this very interesting band inversion. So as you change the width of the quantum well, you can go into limits where S level lies above the P level, but then going through a phase transition beyond which the P level will go above the S level. And so now we constructed a very simple model back in 2006. How to describe this system? It's basically based on 4 orbitals. You can have S level up or down. For P, the most spin orbit coupled level, if you have spin up, you would take LZ equals to 1, which is Px plus IPy. And if you have spin down, you would take LZ equals to -1, which is Px minus IPy. And so for the lowest order, you look only the hopping between S and P with spin up. So the 4x4 matrix Hamiltonian decomposes into 2x2 blocks. And then on the diagonal element, it basically has the level difference between S and P. But interestingly, on the off-diagonal elements, because S and P have the different parity, they can only couple, they cannot couple at a gamma point because K equals to 0, they have different parity, they cannot couple. So when you expand to the linear order, you get some matrix element that linear in K. So this is a vivid example of a piece of relativistic, quote-unquote, Hamiltonian emerges in the low energy sector of condensed matter. This is something I'm always fascinated with. that at the fundamental level, at mega electron volts of the order of mass of the rest mass of the electron, you have the Dirac equation. Then you go to condensed matter physics, which is typically of the order of few electron volts. You have Schrödinger equation. But then when you go to MeV, milli-electron volt scale, you again recover this relativistic dense structure of the electron. Due to the fact that S and P have different parity, so you have linear matrix elements, like the Dirac and Tony. And then on the off-diagonal matrix element, you have the mass term, which has the physical interpretation of the S and P level difference. But that is the fascinating thing about condensed matter physics. In the world of the elementary particle physics, mass of the electron is determined. Here, the mass of this effective Dirac model is tunable, not only in its magnitude, but also you can tune across the sign change, as I explained here. That's by making the quantum well of different width, different thickness, you can actually change the SP level difference, which effectively is like tuning the mass gap. So now, when you look at this material, then the boundary of this material actually look like a domain or twist. Actually, I forgot, I don't have the right slide. You know, in China, we drive on the right-hand side, but in Hong Kong, people drive on the left-hand side. So when the two highway system connect on the boundary, they have to go through a very complicated twist. So this is the same idea. Then on the outside, in vacuum, it's like you have a positive mass, but on the inside, if the mass becomes negative, as the case in mercury telluride beyond a certain thickness, some twist has to happen. And these mass twists actually localize some states near there. So when you look at the, so they actually trap some bound state. But on the x direction, you can actually, kx is a good quantum number. At kx equals to 0, you would have these two states, and they are actually degenerate. But then when you change kx, these two energy level will change, and they will sweep out the dispersion. So at these points, at actually k equals to 0 points at the gamma point, this is a time reversal invariant point. This extra degeneracy is actually very, very special, because this branch then continuously connects the conduction band with the valence band. At this point, there's an exact level degeneracy. And that level degeneracy actually is guaranteed by the Cramer's theorem of quantum mechanics. Cramer's theorem says in quantum mechanics, when you have two spin states, two time reversal states which are paired, they have to be exactly degenerate with each other. So that's why there's always a continuous band inside the bulk which lives on the edge, but which connects the conduction band with the valence. So there's actually a semi-classical picture which explains, similar to this Cramer's degeneracy idea, that if you have these edge states on the sides of the quantum spin Hall effect, you have a spin up which is going forward, and you have a spin down which is going backwards, right? So in principle, it looks like you can backscatter the electron from spin up to spin down. If you have spin-orbit coupling, that could in principle be allowed, and then forward moving becomes backward moving. What is preventing this backscattering? What is preventing this backscattering is one of the most basic and fundamental facts of quantum mechanics. That if you have a spin-1/2 particle and will rotate by 2 pi, for any classical system, if I rotate anything by 2 pi, nothing changes. But in the very strange world of spin-1/2 electron, when you rotate something by 2 pi, you pick up exactly a minus sign. The electron only goes back to itself after 720 degree or 4 pi rotation. So now let's carefully analyze, like in Feynman's philosophy, that we try to sum over all possibilities. So the electron is heavily moving along, and it's scattering around this impurity and being kicked back. But at the same time, it can only move back if the spin is down. So one possibility is that the spin, not only the particle goes around, but the spin also goes around from up to down. Let's say it rotated by pi, the angle of pi. But then the other possibility is that it goes around the impurity in a counterclockwise sense, or its spin rotated by minus pi. So the net difference is pi minus pi, which is 2 pi, which tells you that these two possible backscattering paths always interfere with each other distance. So there's no way for the electron to backscatter because of these destructive interference. And that you see is very fundamental about quantum mechanics. And in a sense, you also sense why there's topology involved. because we explained this strange fact in elementary quantum mechanics class in terms of a Mobius strip that as the end moves around and ends up on the back. So this is something very deeply profound and topological about this kind of argument. And that's the sense, part of the sense of topology. So anyhow, then after our theoretical prediction in 2006, in 2007, so there's one unique group in the world, and that's the group led by Lawrence Mollenkamp in University of Würzburg in Germany. And they actually constructed quantum wells because you can, by NV growth today, control the thickness very well, and they can construct some material which is less. So theoretically, the predicted critical thickness is 6 nanometer in thickness. So you first grow a material which is 5 nanometer, and you find that it's ordinary insulator. So Fermi level is tuning between the gap. The resistance is almost infinite. But then when they go into a material which is 7 nanometer beyond this critical thickness, when this interesting mass gap becomes negative, then it has a conduction band and a valence band, but then have these branches which is continuously connecting the conduction with valence. So then when they did the experiment, tuning the Fermi level into the middle of the gap, which normally doesn't have any conduction, and then they actually see a quantized conductance of 2e²/8, and this number 2 simply counts the number of edges that you have. And it's independent of the width of the channel, which is totally opposite to the Ohm's law, and also more or less independent within a certain range, independent of the length of the channel, which is also opposite to Ohm's. And more recently, there's a remarkable experiment. So this is a transport experiment, and the only sensible interpretation is that it's conduction through the edge. But more recently, there are more Mobius-based imaging techniques, some done by my colleague Catherine Moller, done by ZX, and I just show data by Amir Yakubi. So you take this quantum spin core insulator, mercury telluride, he got a sample from Würzburg, but then put superconducting contents here, and then subject to a magnetic field. So you see superconductivity come here in a very interesting interview. So then you measure the Josephson current across these two superconductors mediated by this interesting topological insulated state. So as you dial magnetic fields, you can measure the different Josephson current as a function of the magnetic field. But it turns out, that's a very well accepted theory, that the Fourier transform of that spectrum, Josephson current as a function of magnetic field, tell you about the spatial distribution of the current. And that spatial distribution, once you're tuned into the topological insulated state, as you see, is that it's peaked on both edges. And if it's inside the conduction or valence band, the conduction goes everywhere. So from these patterns of supercurrent as a function of magnetic field, you can read off the spatial distribution of the current. In one case, it's localized on both edges. And in the other case, when the Fermi level is in the conduction of valence band, it goes everywhere. So this is kind of a beautiful experimental design, which gives you such a striking view space result of this picture of edge state conduction. So now, besides mercury telluride, we would like to find other topological insulator in 2D. Actually, for possible application, 2D may be the most desired. And so you saw from this diagram that it looks like most things may not be topological. But then in 2008, we came up with the idea that you can actually make a topological insulator out of non-topological material. So indium arsenide, gallium antimonide is a very well studied, unlike mercury telluride. It's very well studied around the world, maybe also here at Berkeley. But each one of them is a non-topological material. They have an ordinary gap sequence. But interestingly, when you put them together at the interface, an interesting fact happens. Namely, the bottom of the conduction band of one material sinks below the top of the valence band of the other material. So then there's, even though each material is not banding good, there's a relative banding good. And we predict in 2008 that this material, the combined material, will also become a 2D topological. There is also another interesting desired effect, because out of all semiconductors, indium arsenide has the best coupling with superconductivity, and that's very highly desired in most applications. And only last year, really those group actually confirmed that theoretical prediction. That in this material, that they also see well-defined topological. But still, both of these materials, the gap is relatively small, about 10 million electron volt. So we talk about we got rid of one extreme condition. Quantum Hall requires high magnetic field and low temperature. But now that we got rid of the external magnetic field, we would like to increase the temperature. But if you have a topological gap of 10 million electron volts, it will not work at room temperature. So very recently, we predicted a new material. So you can hopefully you can see here at Berkeley, there's a lot of beautiful work on first principle calculation in this field. This kind of calculation actually can guide and predict which material. So we actually predicted a new material. You all know about graphene, which is a single monolayer of honeycomb lattice made out of carbon. When you go down vertically in the periodic table, at some point it will encounter tin, which lies below carbon in the periodic table. And as you know, the chemical symbol for tin is Sn, Latin for stannum. So we actually coined a new name for a single monolayer of tin called stannine, modeled after graphene. And then, so then we predict that this system will form a buckled honeycomb lattice, where the green ends, both sides are a little bit buckled in the z direction, but still more or less a honeycomb lattice. And we actually predict that in this system, it will be a two-dimensional topological insulator with a topological gap of 300 millielectron volts, 10 times higher than room temperature. It's also very interesting, a natural continuation of graphene research. So we're proposing this material, and a lot of groups around the world are trying to get it. So now, after the two-dimensional topological insulator story, Joe and colleagues have proposed the idea of a three-dimensional topological insulator. Where do we find them in nature? Basically, at the place, the discovery of mercury telluride pointed us in the right direction, because in the lower right hand corner of the periodic table, there lies mercury telluride and a lot of other materials you can make, and then we can systematically study. So one popular material is now bismuth selenide and also bismuth telluride. They have more or less similar structure, and that material form a principal layered structure, just like graphene. But in this case, they're mostly the p orbital in the system. So in the case of mercury telluride, we have an sp level inversion. But in this case, because of principal layer structure, you can form bonding and anti-bonding p orbitals. And by spin orbit coupling, the bonding and anti-bonding p orbitals leads to a band inversion, which is the key to topological insulator behavior. But actually, nature gave us very interestingly 4 different materials, and they have some different property, but they have different strengths of spin orbit coupling. So our theory calculation shows that antimony selenium doesn't have enough spin orbit coupling, but all these 3 have enough spin orbit coupling, so that there's a band inversion that happens. And inside, you have inside between the conduction band and valence band, which are separated by about 300 millielectron volts, there's a single Dirac cone lying around the gamma point. And that's effective theory is described now by 3-dimensional Dirac equation, where this mass gap labels the energy difference between the bonding and anti-bonding p orbitals. When you dial the spin orbit coupling, there's a band inversion that happens, and it traps some topological surface state. So in this very precise sense, the surface state of bismuth telluride is exactly 1/4 of graphene. Graphene has 2 valleys and 2 spins. So altogether, it has 4 Dirac cones. But on the surface of a topological insulator, there's only 1 Dirac cone on the surface. You can prove some kind of a general theorem that any ordinary 2-dimensional material would at least have 2 Dirac cones. So that tells you that if you expose this surface to any ambient environment, something will stick out to the surface, assuming this is ordinary material, which have 2 Dirac cones. That surface state only has 1 Dirac cone, and they cannot kind of annihilate with each other. There's always something left over. But there's also a kind of a fundamental description besides the Z2 topological band invariance that Joe and colleagues have proposed. There's actually a general definition of the sense of topological insulator, which is valid in the presence of any arbitrary interaction in terms of a response state. So if I have a piece of insulator, I can couple that. 20 minutes. Okay. So if I have a insulator, then I can try to figure out what my insulator is doing by coupling these to external electromagnetic fields. So, but then the response I get will be described by something like a dialectical constant and the magnetic permeability. And this is how we can describe the electromagnetic response of any ordinary insulator. So here maybe is the clearest explanation of what do we mean by something that's topological. So if I change the material a little bit, I add a little dirt in my insulator, I replace some iron by its isotope, change other things. Usually, the dialectical constant and magnetic permeability will change slightly if I change the material slightly. So these kind of response are not topological response because I make a smooth distortion, they will change as well. But then there are besides the E squared and D squared effective response of the insulator, there's another possible term, which is E dot B, okay? And that is in general allowed. But E dot B actually is very interesting. You can very simply appreciate by if you did some Griffiths level electromagnetism textbook. So E dot B can relativistically be expressed as F mu nu times F mu nu du or F mu nu times F rho tau times the epsilon tensor. But this E dot B, even though it looks like a bulk term, actually it can be completely expressed when you express E and B in terms of the electromagnetic vector potential as a total derivative. So this immediately tells you that this is kind of a topological term, even though it's a bulk-like term, it knows something about the surface. And so what it knows about the surface, so then the coefficient in front of it, if you normalize properly with the prime structure constants in the front, so it will be theta over 2 pi, but this theta will be periodic. If you shift theta, because this is a topological term, if it shifts theta by 2 pi, it actually does not, even though it changes the action, it does not change the total partition function of the physics, which will change by E to 2 pi I. So that's something very interesting about this topological term. But now if you further impose time reversal symmetry, then obviously theta equals to 0 is one of the possible choices. And that's when your textbook stops. Is if I have time reversal symmetry, because E will not change sign, but B will change sign, and the time reversal symmetry, theta equals to 0. So in a time reversal invariant insulator, usually we don't write down such a term. But interestingly, theta equals to pi is also a choice. Because under time reversal symmetry, theta equals to pi will go to theta equals to minus pi, but they differ from each other by 2 pi, which is period, which doesn't change physics. So interestingly, so topological insulator can be defined by theta equals to pi kind of a response. So that is topological because this is in principle a magnetoelectric effect that can be experimentally measured. But in this case, inside the topological insulator, if you change things a little bit, the magnetoelectric effect will not change, it stays invariant. So there's something physically measurable, which is a topological invariant, and that's the precise sense why this is topological. But that immediately leads to kind of something that goes beyond the original field of time reversal invariant topological insulator. So imagine I have this Dirac cone, and at the Dirac point, the gapless nature of this Dirac cone is protected by the time reversal symmetry. But now imagine that if you coat the surface of a 3-dimensional topological insulator by a thin magnetic layer, it could be doping the material with some magnetic atom, putting on a ferromagnetic insulating film, and so on. But then nature usually, if by symmetry it's allowed, it will happen. So by having a magnetic layer on the surface, it will break the time reversal symmetry, and then it will open up again. Actually, experimentally, people have seen that. If you put magnetic elements on the surface, such as iron and chromium, the original Dirac cone will break up, and it will break up by opening up again. So the naive expectation is that then it becomes really ordinary kind of insulator, because inside it's insulating. Previously, before you break time reversal symmetry, the interesting thing is the surface has a gapless Dirac cone, which is in some sense protected. But now you even open a gap on the surface, it looks like it's insulating everywhere. But there's actually one interesting thing that people tend to overlook. That's if you have a magnetic moment on the surface, magnetic moments can have a domain, right? So then if I have this region spin up, but another region spin back, again, this becomes an interesting kind of a twist. Because then on the interface, on the domain wall, you would expect there's no gap. But not only there's no gap, it has an exact chiral sense. And the chirality is defined by the vector cross product between the surface normal, and so by the right-handed rule, if you point your finger to the surface normal and thumb to the surface normal, one of the fingers to the gradient of the magnetization, your finger will point out to a unique direction along the domain wall where the current can flow. So this is a chiral current. Even if you break the symmetry slightly on the surface, it will lead to this chiral state. So that leads to another interesting state of matter called quantum anomalous Hall state. So imagine that I put the top surface and bottom surface with magnetization. They will all open up a gap. But on the top surface, the direction of magnetization is parallel to the surface normal. But on the bottom surface, it will be anti-parallel to the surface normal. So in that sense, it makes the four side wall looking like a domain like this. And that will have a chiral current. So without an external magnetic field, without any lambda level, in this magnetically doped topological insulator, you can actually have this chiral edge state, which is now only flowing in one direction, and the sense of direction is selected by the direction of the magnetic field. So that leads us to another interesting branch of condensed matter physics called anomalous Hall effect. So when Hall first discovered Hall effect under magnetic fields 10 years later, he also discovered anomalous Hall effect due to magnetization in a ferromagnetic material rather than due to an external magnetic field. So now if we imagine that if I have a magnetic insulator, then it can have a conduction band and a valence band. And very early on, Duncan-Haldane constructed a model in which you have a honeycomb lattice model, but you have a conduction band and valence band, but this time only one chiral branch connecting the conduction band with the valence band. And one chiral branch is allowed because in this case, there's no time reversal symmetry. So in this kind of model, we later did some work on the quantum anomalous Hall effect based on spin-orbit coupled ferromagnetic material. So basically, you can describe this by a two-band model, and any two-band model can be expanded by Pauli matrices and with three vector coefficient, and then the Hall effect of this insulating material is exactly what is called a Sturmian map, or in momentum space. So it's basically a mapping from the momentum space, which forms a torus, to the vectorial direction of a three-dimensional vector, which is the surface of the sphere. So when you make this mapping, it's topological invariant. It's classified by integer, which is exactly a quantum Hall effect without any external magnetic field. You don't need any lambda levels to have quantum Hall effect. But due to the ferromagnetic moment of the material in this insulator, you can actually have a finite quantization. Another picture to see it is that if you have states going forward and backward in a quantum spin Hall effect, but now if you put in a magnetic moment which breaks time reversal symmetry, then it will annihilate one pair of the state and leaving only one chiral branch intact. So this is so there's a natural evolution when you dope a topological insulator, whether it's 2D or 3D, by magnetic elements, it will actually form a two-dimensional quantum anomalous Hall state, which carries the chiral edge currents without any external magnetic field. And we actually predicted concrete materials we proposed chromium doped bismuth ferrite. And not only the first surprise is that these will form a ferromagnetic insulator, which is already very, very rare in nature, but we further predicted that the ferromagnetic insulator we exactly have a quantized Hall conductance or Hall resistance. And the mechanism for this ferromagnetic insulator can be basically explained by two somewhat complementary pictures. So remember that you have a surface state which forms a Dirac cone. So in condensed matter physics, there's a well-known idea that if I put magnetic moments into a conducting material which has a Fermi surface, it mediates a magnetic interaction which oscillates at a periodicity of 2km. But now the interesting thing is that when you put the magnetic moments on the surface and put the Fermi level exactly at the Dirac point, there's no km. So the magnetic interaction mediated by the surface Dirac electron does not oscillate. Which sign does it have? We actually calculated it's always ferromagnetic. So actually the surface prefers to order ferromagnetic rate because the effective interaction doesn't oscillate. It's always ferromagnetic. So that's one very simple picture to understand why when you dope any magnetic element into, there's a very, very big field called dilute magnetic semiconductor. People putting things like manganese into gallium arsenide. But when you don't put in enough, it doesn't order magnetically. When you put a lot, the effective mediated interaction oscillates very wildly in sign. It becomes a spin glass kind of thing. But on the surface of a topological insulator, there's only one sign. It's always ferromagnetic. So you can put in quite a lot of chromium or magnetic elements. It always mediates a ferromagnetic interaction. That's why it's easier to realize that magnetic insulator in a topological insulator. And there's some other complementary pictures. But roughly speaking, this is the mechanism why they like to form. So this time, unlike in the case of quantum spin Hall effect, 206 was predicted the material already seen in 207 experimentally at the University of Würzburg. This time it took a little bit of time. The material was predicted in 2010 in a science paper, but then only last year, there's a group out of Tsinghua University which first saw the quantum anomalous Hall effect in chromium-doped topological paradigm. So this is really, I hope to convey the sense of excitement to you in condensed matter physics. This is a search that has lasted more than 100 years. That since the discovery of Mr. Hall of the Hall effect, a little bit later he discovered the Anomalous Hall effect, knowing that there is even in a ferromagnetic material without any external magnetic field, time reversal symmetry is already broken. It allows to have a Hall effect in a ferromagnetic material. This effect was discovered in 1881. Still today, theorists are still discussing the origin of it. Joe was just telling me he is doing some very interesting work on that. But then, in addition to these two Hall effects, there's also the spin Hall effect. In this case, it's a spin orbit coupled material with respect time reversal symmetry. So when you pass a current in this direction, you're not allowed by symmetry to have a voltage, have a charge imbalance, but you can actually have a spin imbalance on both sides. And that effect was also experimentally observed. But now, interestingly, to each one of these three classical Hall effects, there's a quantum version. And the quantum version in 1980 was the discovery by Klaus and Klitzing, seeing that in magnetic fields, they form lambda levels, and they give rise to a precise quantization of the Hall effect. In 2006, we predicted the quantum spin Hall effect in mercury telluride. In 2007, it was experimentally observed in mercury telluride quantum realm. This we predicted in 2010, but in 2013, last year, it was first observed in Tsinghua University in China. So what exactly is the experimental signature? So now you make this, you grow on a substrate, this topological insulated film, but now this time not only putting bismuth telluride, but also put some amount of chromium into the system. And now you can change, you measure the Hall resistance, longitudinal voltage, transverse voltage divided by longitudinal current as a function of magnetic field. So first, when you see a hysteresis loop in the Hall effect, it's a very good indication that the material is ferromagnetic. But most interestingly, when you look at this hysteresis loop at zero external magnetic field, there's still a quantized Hall effect. So the magnitude of this is 1 in units of h over e squared, which is the resistance function in basic quantum mechanics. So this is the more detailed experimental data. As you sweep the magnetic field, you actually see a hysteresis loop in anomalous Hall material. You see this all the time. Except here, there's a plateau at h equals to 0, 1 in units of h. But when it's when it's switching from the positive domain into negative, opposite pointing domain, at the same time, the longitudinal resistance actually has a peak. So there's some interesting theory which could explain it. But that still looks a little bit like the Hall effect. The interesting thing is that you can now put the external fields at 0, but now you sweep the gate voltage. Well, remember, when you sweep the gate voltage, you can go from conduction band to valence band through this topological insulator regime. And as they sweep the voltage at 0 external magnetic field, they actually see it develops a Hall conductance plateau at 1 square. So at that time, the longitudinal resistance is still not quite going to 0. My colleague, David Gordon, has done more experiments. It's getting very, very close to 0. It's a very precise quantization in the absence of any external magnetic field. So this is the discovery which completes the quantum Hall trio, quantum Hall effect, quantum anomalous Hall effect, and quantum spin Hall effect. Great chapter in quantum metaphysics is now complete. So now we have done some more work on these, and basically we try to see not only there's a single lane possible, we're doing some theoretical work using more subbands in this two-dimensional structure so that you can get multiple parallel states in this quantum. So that can go to higher conductance plateau. A very interesting thing we observe is that as a function of thickness and the amount of magnetism or the size of the exchange gap you put into the system, there's actually many possibilities. You can either be at Hall plateau 0, 1, 2, and so on. But here, notice there's an interesting development that as I increase the direction, the size of the ferromagnetism in the sample, I go to higher conductance. So you may think that this is analogous to quantum Hall effect. I change the magnetic field, I go to different plateaus, but they're going opposite direction. If I go increase the magnetic field, I go to a lower conductance plateau. By increasing the magnetic field, I increase the degeneracy of the lambda level. Actually, I go to a lower conductance plateau. In this quantum anomalous Hall system, where I increase the magnetic moments, it goes to a higher conductance plateau. So there's at least something qualitatively different between ferromagnetic insulated induced quantum anomalous Hall effect and lambda level based quantum Hall effect. And we actually have some theory which explains the non-local conductance in this system, which is also being measured. Interestingly, you saw that previously, as I switched the magnetic domain, the Hall resistance jumps from 1 to -1 in a very abrupt step. But we actually predict theoretically, which is remains to be seen experimentally, that between them there's also a 0 conductance plateau. A lot of Princeton group claim to have seen some basic signatures of the superconducting quantum group. And then when you analyze these peaks, there's actually some. This is a textbook quantum critical phase transition, and the width of these plateaus, width of this peak and the plateau transition should all obey some universal scaling laws, which should be the same as that of the quantum Hall. They give you another model system study. So now let me switch very quickly to the topological superconductor. A very simple cartoon picture to understand the relationship between the two is that here is the cartoon picture of the quantum Hall effect, where you have these parallel edge states, and quantum spin Hall effect, where you have the so-called helical edge state, where spin up is going around clockwise and spin down is going around counterclockwise. So here you have quantum Hall effect on the edge state. You have momentum k and energy, which is only one branch, and that's the sense of chirality. The dk, the velocity, is always positive in the upper sense and always negative in the lower branch. So you may think this is already the smallest system you can have. I have one dimension, I don't have spin, I can only go in one direction. What can be possibly smaller than that? There's actually a duplication in this system. because this is after all insulating state. So I feel the Fermi level up to E equals to 0. All the negative energy states are filled, all the positive energy states are empty. But now I can take the electron from here to above from E less than 0 to E greater than 0. So I can have two charge types. I can have particle type and the whole type. And that is actually a duplication which you can, in principle, eliminate. And that's actually eliminated in a chiral superconductor. So if you have a superconductor, which is paired in P plus IP fashion, in L equals to 1, but Lz also equals to 1, then it has a P plus IP has a full pairing gap in the bulk, but it actually has a gapless chiral state on the boundary. Now, because the superconductor is a linear superposition between particle and host, on this boundary, not only is chiral, it only has one particle type, and that's called Majorana fermion. So this is called chiral Majorana fermion on the boundary, and this is T breaking, but then there's also a T invariant counterpart. You can think of it as P plus IP for spin up and P minus IP for spin down. So in the case of a three-dimensional version, we actually showed that the phase of the superconducting order parameter becomes what is called an axion. So you previously have seen that in topological insulator, F(0) has a coefficient of theta equals to pi, but now for topological superconductor, the coefficient actually is a field, which people in particle physics call axion. And then it's actually exactly the phase of the superconducting order parameter. So that actually makes me very happy. It looks like condensed matter system, as Joe's introduction says, I started out in high energy physics, but now suddenly this condensed matter system becomes a laboratory to test many interesting examples of the. So actually, let me quickly wrap up. So we are now faced with a big crisis in information technology, in the sense of power dissipation. As we go to smaller and smaller technology nodes, the power dissipation is getting more and more severe. And so the basic picture is that because electrons move very randomly inside the semiconductor, just like you have race cars that moving in a crowded marketplace. But if you say that this is the right analogy, the right solution for the problem of power dissipation, for enabling us to go to smaller dimensions for semiconductor features, is to build a highway system. And this topological insulated state looks like exactly the highway-like system, that you have spatial separation of oppositely counterpropagating traffic. And actually, in the case of quantum anomalous Hall state, the number of lanes you have is exactly a topological invariant. It's not something you can easily change. So ideally, we would like to build the electronics that are robust, and they are just the conduction properties are guaranteed to exist, even if you disorder the system slightly. So this is one of the possible applications. And as you know, inside the semiconductor, there are transistor layers and interconnects, and there's actually a DARPA project funding this highway system to enable the interconnects inside the semiconductor. Actually, this proposal is already went into the international technology roadmap. Another very interesting possible application for topological insulator, something Joe also worked on quite early on, is that interestingly, all these topological insulators are also very good to thermal electric material. So thermoelectric material can generate useful electrical current out of waste heat as long as you have a temperature gradient. And so this is the standard picture. But why we don't see it everywhere is because its efficiency is still very low. But its efficiency actually can be conventionally expressed by a dimensionless quantity called the ZT figure of merit, which has conductivity, the Z-back coefficient, and thermal conductivity. So now the reason why we cannot increase them is because there are intrinsic relationships between them. For example, a very famous thing is called the Wiedemann-Franz law, which governs some relationship between electrical conductivity and thermal conductivity. But this is a formula almost everyone writes down. But we suddenly realized that this shouldn't be the right formula. you should actually express not everything in terms of conductivity, but in terms of conductance. You have, instead of conductivity, you should have conductance, and instead of thermal conductivity, you should have thermal conductance. You say, why bother? I just write by Ohm's law or Fourier law how conductance scales conductivity. But that's only true in ordinary material. In a topological insulator, conductance doesn't scale according to the geometrical scaling of Ohm's law. So suddenly, in the figure of merit, you have another tuning parameter. Previously, we're very frustrated because it looks like there's some intrinsic relationship between them, and no matter how hard you work, it looks like we're stuck at z equals to 1. But now, we actually should have another tuning parameter, which simply is the geometrical proportion. We also have a proposal how to increase the z-back coefficient by tuning the Fermi level close to the bottom of the conduction band. The z-back coefficient measures the asymmetry between the conduction band, the states above the Fermi level and the states below Fermi. But those surface states, topological surface states, would have a very short lifetime above the Fermi energy because they can easily scatter into the bulk. But on the other hand, they will have a very long lifetime for states below the Fermi. So that actually can also increase the z-back. So we hope that topological insulator can be useful also as thermoelectric. So now let me put up the last slide. So these fields, I hope you get a sense, is developing very rapidly. Theory actually can play a useful role, making some useful predictions, which are seen experimentally. But also a very exciting aspect of this, it seems to connect many, many branches of physics. First, in condensed matter physics, we have the traditional semiconductor physics, but these topological insulators are, in some sense, narrow gap semiconductors. Mercury telluride was called narrow gap semiconductors before. This dopant physics, NDE growth, these standard arts of semiconductor physics suddenly become very, very useful. Magnetism is a very important branch of condensed matter physics, but people develop spintronics, dilute magnetic semiconductors, magnetic layers, and they all play a vital role in the story of topological insulators, especially in quantum anomalous Hall. The field of superconductivity and superfluidity, very, very important in condensed matter physics. Now we see there's a topological output, there's new states of matter, which are in some sense topological superconductors and topological superfluid. I forgot to mention that helium 3b phase is actually predicted to be a topological superfluid with a Majorana cone on the surface. So that connects deeply to a very well-established branch in condensed matter physics. Quantum Hall effect, of course, is like the inspiration for doing quantum spin Hall effect and topological insulation. Also, heavy fermion, these materials involve heavy electrons. They actually have heavy because in one sense, because heavies, they are actually made out of heavy elements with heavy electrons, and they have very strong spin-orbit coupling. And there's a material called samarium hexafluoride, which is a heavy fermion material, which are predicted to be a topological tunnel. In cold atoms, there's a lot of very interesting work trying to realize engineer spin-orbit coupling, realizing the topological. Another very interesting connection is that I hope I explain a little bit is that the connection to particle physics. A lot of the ideas came from particle physics, but now we can give something more because in condensed matter physics it's like a laboratory where you can have many tuning parameters, and some things that you need thought you need to build a huge accelerator for actually can exist on the tabletop experiment in condensed matter physics. In particular, because of this E dot D effect, if you put the electric charge on the surface of a topological insulator, the image is not just an electrical charge. The image is also magnetic monopole. So that's a very striking effect. Monopole hasn't been seen, but if we can do the experiment in topological insulator, we can limit the effect of monopole. I explained that in a 3D topological superconductor, the phase field of the superconducting order parameter is actually an Axion field. This Majorana fermion, there's a particle physics experiment going on, trying to see if neutrino is a Majorana fermion. Still, jury is out. There's an experiment called neutrino-less double beta decay. People try to perform the experiment to see if they're Majorana fermion, but they naturally exist inside topological superconductors. and they could be used for topological quantum computing. Beautiful ideas out of the string theory are now having more and more applications in this field. For example, the concept of modular invariance is very central to string theory, but now they're used to detect topological stability in fact in topological system. And maybe the most provocative question one can ask is whether we live in some sense inside a topological insulator. And that can kind of explain why the states where the most natural energy scale is either the Planck mass or gravity unified scale, but the particles we observe in our world are much, much lighter than that. So maybe we live in some kind of a surface state of a 4+1 dimensional or higher dimensional topology. So that, with that I can see. Yes. Yeah. Yeah. Right now it's that's the temperature. So we hope that we can get into this regime that because these materials still have a relatively small gap. So let's say standing will realize this 300 millielectron volt gap, then the bulk will be really insulated, and then they will be high resistance. So a lot of engineering will be done, but I dare to make a prediction that topological insulator behavior will be observed or in this high wavelengths at room temperature before superconductivity. Because that's more predictable. There's more also a band gap. We see a lot of higher band gap material, very few large superconducting. No, we shouldn't dope. We should be in the between the conduction and valence band when the bulk is.
Related question.
Yeah.
For example, standing at room temperature.
Yeah.
You have the quantum signal that modes going in both directions.
Yeah.
And I might think that even if it's sort of electronically protected, I think elastic.
Yeah. So we want So but somehow this state seems to be more robust than we initially thought. So one indication is that they even survive at large magnitude. So one thing, and there's also some theoretical work after our papers that they should be a little bit more robust. But also another avenue is to make standing functionalize with magnetic elements to go to quantum anomalous halls. So there are also more materials, stoichiometric materials predicted for quantum anomalous halls, which have energy gap as large as 50 energy. So the material research is getting into an interesting phase. There's some pretty good theoretical prediction, but I would say quite strong motivation.